Good afternoon, class. This is going to be a lecture for college algebra on functions and transformations of functions. So before we begin, we're going to have to talk about what is a function. And to do that, we'll have to talk about what is a relation. So because a relation is a kind of, a function is a kind of relation. It's a special kind of relation that fulfills a certain property. So what is a relation, first of all? So let's say given two sets, we'll say set A, which we'll depict as this circle, and set B, which we'll depict as this circle. A relation is a rule associating the members of A with members of B. So let's make up some members for A. Let's say we had A, B, and C in there. And then let's make up some members for B. Let's say there was 1, 2, and 3 in there. And so if I had a rule that associated one in A with one in B, I might draw an arrow that connects them. And so we would say that this relation associates A with 1. And so we would write the ordered pair, A1, and say, well, that is in the relation. And likewise, if there was some other rule, maybe associating B with 3, I would write B3 this way. And last one, if I had C associated with 2, then we would write C2, maybe this way. Now, in a relation, there is no harm in saying, well, I also want to associate A with 2. I would just write another ordered pair, A2. But this is exactly the kind of thing which is forbidden. Notice also that I've associated every single element of A to an element of me. Nothing got left out. Now that, depending on one's definition of a relation, may or may not be true. But for the rules that we're going to talk about, every element of the first set will be associated with an element of the second set. Now, for the purpose of our discussion, I'm going to make B just a little bit bigger. I'm going to say, well, maybe B has this other element 4, and no element from A got mapped to 4. That would be okay. That would be fine. That's still a relation. It doesn't have to hit all of B. So these elements here, we would call this the domain. And B is not the range, it is a piece of, it is the place where the range lives, right? The range is just the values of B, so just these guys here, not the 4, that get used. It's the set of all the targets of the relation. The whole B is called the codomain. We really don't need that terminology for this class. But I'll just say it does have a name, the codomain. Okay. So let's be specific. Our definition for the domain of a relation are the values which are assigned, which are mapped, we sometimes say, by the arrows. And the range are the values, the range These are the values that the first values are mapped to. So we'll say the values which are the targets of the domain. So we think about the input as being the domain and the output values which get hit as being the range. So just to give a concrete an example, right? The domain of this relation that we've specified was A. That is to say the set A, B, C. And the range, on the other hand, are only the values that get hit. So the values that are assigned to the values in A. And so that's just the set 1, 2, 3. We don't include the 4, right, even if it was there. So domain are the values that get used, range are the values that get hit. So now let's talk about a function. So what is a function then? Well, a function is a relation that assigns only one. Assigns only. This is the main thing. It can only have one element of the range to each element of the domain. And that isn't to say that some things in the range won't get hit twice. They could. What we mean is that the function there is only a single value for each input. Maybe we use the same value. So let's look at an example to kind of suss out what I meant by that. All right, let's take our old A and B again. And let's say this is A, B, and C, and let's say this is 1, 2, 3, 4 again. Now, if I have a relation which maybe says A goes to 1, B goes to 1, and C goes to 4, is this relation a function? Think about it for a moment. The answer is yes. Right? Every value, A gets to 1, B gets to 1, and C gets to 4. There is only a single value, 1, that's assigned to A. There isn't some second value like A2 in the other one. This would be disallowed. You're not allowed to assign another value to A. We say that a function is monovalent. It only gives one value for each input. Now that could be repeated. That's okay. It's okay to repeat values of the range as long as you don't give different values of the range to the same input. That's the issue. So if I was to ever draw another arrow coming out of here, that would not be a function. So frequently in this class, we'll either be dealing with functions given in terms of equations. But for now, while we're getting used to this idea, let's still consider finite sets, because equations really map the whole real number line to some other set of numbers. So let's just imagine another example. Let's say we have a relation given by ordered pairs. And let's say we had 2, 3, 3, 1, 2, 4, and 3, and 4, 6. So what would my domain be? Well, it would be the set of numbers 2, 3, and 4. That's all that gets used. What would my range be? It would be the values that got hit. 1, 3, 4, and 6 all get hit. Is it a function? No. How do we know it's not a function? It's not a function because there is uh, a value 2 which gets 2 inputs. The value 2 maps both to 3 and it maps to 4. That's not a function. Now let's another example. Let's consider a function defined by an equation. So the usual syntax for this is to give the function a name, to say what it's going to take as an input, so, and then say what I'm going to do to that function as an output. So we would think of this as the input, this as the name for the function, and along with the idea, we have these rules that go along with the name. We have these rules. What are we going to do to our input? Well, f is going to square it and then add 3 to it. That's the rules of this game. You put in f, and your output, which you could consider both of these to be the output, really, either the whole thing f of x, or this stuff that's on the other side, right? These are the rules that tell you what to do to the input. And they're equal to each other. So yes, of course, they can both be considered the output of what you would get plugging in some x. So what's a natural domain? Let's say that our domain was the whole real number line, right? The whole thing, minus infinity to positive infinity. Is there any reason why I couldn't plug in a number in for x from the number line? No, there's not. And what we'll learn is that this is actually the domain of all polynomials. There's no obstruction to taking a number and taking it times itself a number of times, adding and subtracting it from other terms, multiplying by coefficients. Polynomials have no issues, no restrictions on their domain. Let's take a look at the graph of this function. Right, we are at +3, and we have a square, which goes over 1, up 1, and then over another one, and up 3 more. Just get a good sketch here. That's all I'm looking for. And so we could ask now about the range. What is the range of this guy? What are the y values that get hit? Well, the y values that get hit are precisely these positive y values. The domain, any x value could go into this assignment, right? These rules take in a set of numbers, the real number line, and they assign to that number some other number. So they're a function from the numbers to the numbers. They take the set of numbers to another set of numbers. But which numbers get hit, right? It's not all of them. This goes only so far down, and then it only goes as far down as 3. 3 is the lowest number. And in fact, we include 3 because if you plug in 0, you get 3. And then it goes all the way up to infinity. That would be this thing's range. So here is my domain. And here is my range for this function. How can we tell it's a function, right? One way to tell something is a function, so how to tell a graph is a function, right? Remember that we need one single value for every x value. So x can only go to one single value. What we say is that if a vertical line, any vertical line, passes through the curve in at only one point, one and only one point. So this is called the vertical line test. And if a vertical line passes through this function only once, then it, or through the curve of this function only once, then it is a function. Then the relation is a function. So this one is definitely a function. I said that in the beginning, but also we can now see it because of the vertical line test. So just to write that down, if every vertical line through points in the domain hits the curve in only one spot, then the relation is a function. So let's look at something that isn't a function. So what's not a function? So example, let's take the circle. Right, the circle actually can be described as the set of all x squared plus y squared that is equal to some radius squared. Let's take the unit circle. Let's say it has radius 1. Well, is this a function? Well, no, definitely not. Not a function. It's a relation. It assigns points on the x-axis to points on the y-axis. That's true enough. But for every x point, except for these two endpoints, we're actually assigning two values of y, a plus and a minus one. Right? If I go to solve this for x, what I'll get is x squared is equal to 1 minus y squared. And from there, what I could get is x is equal to plus and minus the square root of 1 minus y squared. Ah, that's two values. Not a function. So a vertical line, for example, would hit this in two spots. As long as it hits anywhere in more than one spot, it is not a function. So let's talk a little bit about specifically a kind of function called the linear functions. So linear functions are the lines on the xy plane. And for now, excluding some of the vertical lines, let's talk about lines of a certain form. So this is functions whose graphs are lines. And there's only those two cases. Either they are vertical, in which case they are not functions, because a vertical line would hit a vertical line in every spot. And then there's other lines. So for other lines, we can always write them in this certain form, y equals mx plus b. And what we'll do to write this as a function is just say, well, we'll call that f, right? F of x then is equal to mx plus b. These are the rules that we're going to do to every single input of x. In fact, you should just think about the y as being f of x. Some people, some books will even call this the f of x axis, and this the x. I don't necessarily like to do that because what I want to distinguish is that you have these two axes and the curve that goes through them, right? Let's say it's still a line. Let's say we're talking about lines here. These values are what I want to think of as f of x, right? The y value, and put it over here because it's a y value, right? These particular y values, f of x, is what I would get if I plugged in a certain value of x. We have the usual meaning for each of these. This is the slope. It's the constant amount where if I go over on my line, let's say I go over by 1 unit, I'm going to go up by m units. And if m is negative, I'm going to go down by that many units. So we often think of this as being the rise over the run. I like to think about, number one, running to the right, because we want to go to the right by 1 and see how much we go up or down. I like to think about it this way. If I go right by 1 unit, I'm going to go up, then I'll be going up by 1 unit, or negative, I'll be going down by m units in order to stay on my line. There are some other good formula for slope that we should know. For example, the change in y over the change in x, where this symbol here means change in. How do you calculate change? Well, we really just take the difference between 2 points. Maybe I started at point 1 and I went to point 2, right? Maybe we start here at some x1, y1, and we wind up here at some x2, y2. Well, how far along in a run did we go? We went over by x2 minus x1. How far up or down did we go? Well, that's calculated by y2 minus y1. The other letter in the formula here, b, is the y-intercept. It's the value f of 0, right? How do we see that? Well, if you plug in 0, this term goes away completely. So where is f of 0? Well, here is x equals 0, right? So f of 0 is this guy right here. And this is what we would call b in the formula. The number that would be in b's position right here is going to be the same as the value on the y-axis that the line hits, the so-called y-intercept. Let's talk real quick about point slope form. Right, if I have, again, some line, and I know a fixed value on that line, let's call this x1, and then this one y1. If I want to know how far over I go to some new value of x, what is the corresponding value of y? And these could be any values. I could imagine this is variable. Maybe it's over here, maybe it's over there, but it's some new value of x. Well, we actually have a way to calculate that if we know the slope, right? We know that any value, y minus y1, divided by this new x minus x1 is going to give me the slope. And so if I just rearrange this slightly, what I get is y minus y1 is equal to m times x minus x1. And this is point slope form. Let's look at an example that uses point slope form. What line goes through the points let's make up some points here. Let's say 1, 3, and negative 2, 6. We could graph that to just try to get a little handle on what we're looking at here, right? Here I am at 1, here's minus 2, here's 1, 2, 3, and 4, 5, 6. So I'm at 1, 3, or I'm at minus 2, 6. A little bit more on target there. Okay. And now the question is, what is the line that goes through these 2 points? And there's only one, right? As soon as you pick a single point, there's just this one line that goes through it. And it looks like that y-intercept is passing between 3 and 4. It's not on one of those lines per se. Let's see if we can't calculate it. So I know we'll take this to be my y1, y2. Oh, sorry. This is an x value, x1, then y1. And we'll call this x2 and y2. So then I can calculate my slope from that, right? The slope is going to be y2, minus y1 over x2 minus x1. And that's going to be 6 minus 3 over 1 minus minus 2. Oh, I beg your pardon. Minus 2 is the second value. We need to keep this order straight. Minus 1. And what do I get there? I get 3 over minus 3. And that's just minus 1. So perhaps my graph is just poorly drawn here. Let me erase that and try again, because if this is truly a slope of minus 1, then I have made a bit of a boo-boo. So let's redraw more carefully this time, and perhaps to scale, right? Maybe something was wrong with my scale. 1, 1, 2, and then 1, 2, 3, 4, 5, 6. And I plot my points. 1, 3, it's here. And minus 2 up to 6, that should be here. And now if I connect them, aha, okay, that's a little bit better. There we go. There we go. And yes, I'm sketching, right? So this isn't going to be 100% exact, but oh man, that other one just was not working for me, right? And I knew it couldn't. As soon as we got this integer slope, right, that tells me that when I go over by some whole number of steps, I'm going to go down by the same number of steps. So let's get an equation for this line, right? We can use point slope form for that. Y minus y1 equals m times x minus x1, where now my x and y without the subscripts are variables. And we can plug in our other numbers, y minus 1, right? That was our y1. Minus 1 here times x minus x1. Excuse me, this should say x1 here. Be in accord with my formula. And gracious me, so this is I'm messing this up. So this is y1 is 3. Yes. And this is x1. So we subtract 1. And from here, we have an equation. Now we could just kind of get this in slope-intercept form if we wanted to. So we distribute this to each term. Minus 1 times 1. Okay, well, that can clearly be simplified. This is minus x plus 1. And over here we have y minus 3 still. So in order to solve for y, I have to add 3 to both sides. And then we get y is equal to minus x plus 4. And checking our graph, we can see this does indeed hit 4. All right, last thing before I take a look at some of the worksheet problems, let's talk about transformations of functions. So transformations of functions are going to let us take some parent function. Let's get an example going on. Let's say f of x is equal to um, x squared, right? And what would the graph of that look like? Probably getting used to seeing the graph of a parabola right now, but let's throw him up here. Just roughly speaking, I don't need to plot a bunch of points. I just want to show you the shape of the thing. And let's consider what would happen if I took and made some new function. Let's say, g of x. What would happen if I just added 1 to the outside of my function? So notice this is f of x, right, plus 1. What does that do? Well, that would take all of my y values, all of my outputs, and increase them each by 1. So 0 would go up to 1, and whatever 1 was would go up to 2, and we would just increase the function by 1 everywhere. So it had the effect of shifting it up by 1. So this shifted f up by 1. On the other hand, let's take a look at some other function. Let's take a look at h of x. And let's say that is f of x plus 1. Okay. So let's look at what would happen here, right? Specifically for x squared. Right? You would wind up with let's make a small table here, right? So what would happen for different values of x to my f and my h of x? All right, well, let's just do -2, -1, 0, 1, and 2. Then the squares are 4, 1, 0, 1, and 4. And what about h? Okay, well, this is -2 plus 1. We compose that first and get -1. Squared is 1. And I plug in -1. Plus 1 makes that 0, so this is 0. I plug in 0, plus 1 makes that 1, so the square is 1. I plug in 1, plus 1 makes that 2, and f of 2 is 4. I plug in 2, plus 1 is 3, squared is 9. So look what happened. It seemed to shift everything back. It shifted all of the y values up a little bit, which means into the negative numbers of x, right? Now I'm getting to the h values sooner. Smaller values of x, like -2, are getting to, or let's say -1, right, are getting to 0 before plugging in 0 did. That was what I needed to get 0 out of f. I only need to plug in -1 to get it out of h. So what does that look like? Well, here at -1, I would have 0. And then at 1, I would have 1. And so on. It would go up like this. And likewise, if we were to keep going to the left, we could keep going, and we'd have something that looked like this. So what just happened? What happened to the blue curve relative to the red curve? Well, this one shifted to the right. Or sorry, to the left. The green curve shifted it up, and now adding 1 inside shifted it to the left. So this shifted f of x, shifted that whole curve left by 1. And maybe that's surprising that we put a positive number in, and yet it shifted towards the negatives. But that just is because the inputs got bigger, and so they arrived at their y values more early. It's sort of like if you add an hour to your alarm clock on daylight savings time, you lose an hour of sleep because you're getting to those values of time sooner. Okay, so with all that in mind, let's go take a peek at the worksheets for this section. I have copied over a few of them here, and I will work them out now for you. Well, first of all, let me lock them in place so they don't slide around on me. Oops. Can I just highlight them all at once? That would be so nice. Okay. And now diving back in. It shouldn't move around now when I move my board. Okay. So let's just go through this one step at a time. Here I've got a relation. It's defined by these ordered pairs. What's the domain? Well, the domain is all the first values. -10, -6, -2, 3, 8, all good. What about the range? The range is all the second values in the coordinate pairs. 13, -5, 18, 13, I don't need to list it again, and 16, right? We're just looking at sets. We don't have to list repeaters when we list our range here. But is it a function? Yes. Remember, having two values in the range, this is okay. The problem is if we have two matching values in the domain that give different values in the range, that is not a function. So yes, this is a function. Does this equation define a function of x? No. No, this is a circle. Oops. Let's draw a better circle than that. This is a circle, marginally better circle, with radius 2. You don't need to know that. You could just try to solve for x, right? X squared would be equal to 4 minus y squared. And the full solution, the full inverse that gives you every value of x would be plus and minus the square root of 4 minus y squared. So this is two values. As long as y isn't plus or minus 2, then it's one value because the square root of 0 is 0, plus minus 0 is 0. And those two values relate for every value of x to some 2 positive y and then some other minus y down here. So no, this is not a function of x. It's a relation between x and y, but it's not a function. Now, does this describe a function? Yes, it does. There's only one value that you get. You plug in x here, you get one value back. You don't get multiple values. Same thing. If I times it by 2, if I add 19 to it, if I add these together, there's only one value produced, right? And that's what makes a relation a function, is monovalency, having only one value for every input of x. Okay, so now we have just the principal root, just the positive root of whatever this is going to be. So this is also going to be monovalent. Remember, we need a plus minus in front of it to make this have two values. And they want us to calculate the following values. So whatever I have in my input position here, I'm just going to plug that into the function. So in other words, this is the square root of 6 minus 2 plus 2 times 6. And that's going to be the square root of 4 plus 12, which is 14. Now, notice that either we are going to allow complex numbers or this one has no meaning, right? If we don't allow complex numbers, then I'm going to have the square root of minus 19 here plus, minus 34. And that's okay. This is weird, But we saw a way to deal with that, right? This would be negative 34 plus I square roots of 19. And that's fine if we want to allow complex numbers. If we don't want to allow complex numbers, minus 17 might be forbidden. For example, if I were to go to some kind of graphing ensemble, like Desmos, and I were to ask it about what about when, I don't know, f of x was equal to the square root of x minus 2 plus 2x. I didn't really like square root. There we go. And we could look at a graph of this thing. And notice that before the value of 2, right, for values smaller than 2, it just refuses to graph it. It says, no, I'm not going to do that. That's not a thing. That is not in the domain, right? So if I want to keep it real, so if I want then the square root, then we have to keep the argument positive, right? We have to keep the argument of the radical x minus 2 has to be greater than 0. In other words, x has got to be greater than 2. So if we want a real valued function, then we have to restrict this to our domain. If we want a complex valued function, that's fine. Then any number could get square rooted. But if we specifically don't want that, if we only want to keep real values, then we have to control what values go into the argument of the radical. Right? They can't be negative into an even indexed radical or we get a complex number. What about 83? Well, what's the square root of 83 minus 2 plus 2 times 83? Square root of 81 is 9, plus 2 times 83 is 166. So this is going to be 173. Here we have not a number, but some other values plugged in. This is not a big deal. All you have to do is replace where you saw an x with now whatever this is. Right now we have some value x plus 6, which is inside the radical. So everywhere I saw an x before, I'm going to say x plus 6. Minus 2 plus 2 times, another x. So we replace that with x plus 6. And that's it. This is all they want. We could simplify that a little bit, though, obviously, right? We have the square root of x plus 6 minus 2 is x plus 4. And distributing that 2, this is 2x plus 12. What about minus 4? Same idea. Same idea. We're composing the function that is the square root of x minus 2. But now my x, the role of x is being played by x plus 4, minus 4. So we need an x minus 4 to stand in wherever I saw an x before. And I'll just leave that. That can be simplified. Okay, so now we're going to determine a few of these properties of functions from the domain and range. From the graph of the function. So determining domain and range from, for example, the graph of the function. And a few other key points about it. So what do I see? Well, first of all, let's mark that y-intercept. That's right here. That fellow looks like 2. right? It's the coordinate 0, 2 on the plane. The y-intercept is what we get when we plug in 0. What about the x-intercepts? Well, I think that we're going to have to just content ourselves to estimating these because they didn't really give us an equation anywhere, right? They didn't tell us how to figure out what those were if we couldn't see exactly what they pointed to. And they're sort of between these two numbers. We can approximate them, though. Let's say that this x-intercept here is approximately -2.5, a little bit more than -2.5 in the negative direction. So let's say this is something like -2.7. And what about this other one over here? Well, that looks a little bit bigger than 3.5, halfway through 3.5. So let's say this is approximately 3.8. Right? Can't do much better than that unless they told us A, what this curve was, what's the equation for it, and then I could just plug in or solve for 0 and figure out what that x value should be. Or if they had made it more clearly hit one of the tick marks, then we would know what it was. What about domain and range? Right, so what are the x values that get hit? Now the idea is you're led to believe that this goes on doing what it does forever, right? So it keeps on going after this, right? It doesn't stop at the edge of the graph. It just keeps on going. And what x values will it sweep out as it keeps on going? Well, all of them, right? These all have x values associated with them, right? X values are getting mapped to y values all along here. And then this goes along, along, along. It's going to keep going and map out all the x values in this direction. So what's my domain? All of the real number line from -infinity up to +infinity. What about the range, though? So the range, right, we're going to hit all of these low y values. Everywhere over here hits some y value that's very small. And then as we proceed along the x-axis, we hit other y values until we get up to this value. And then we just hit 2 over and over and over again. And then finally we start going down again. So then I just hit these values again. So what did I sweep out here? Right, I marked off all my values from -infinity all the way up to 2. And I include the 2 because it looks like it hits that 2. So we use a bracket there. How do we evaluate these expressions? Well, we just look at what the input would be and we read off what the y value is. So for example, for -3, here I am at -3. I look down, I say, all right, well, that's my y value. Where does that come from? Ah, that's -1. So this would give me -1. Likewise, if we want 0, that's what the y-intercept is, right? This would just give me 2. If I was at x is 0 and I went up, 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 what's my y value? Where does it hit the curve? Right there at 2. And then what about f of 2? Well, this is the same idea, right? We go to the x value of 2. We look up or down to find the curve. There it is. And what is that y value? It's also 2. This says now something different, though. This asks the question, what is the x value that gives me -1? So hang on, we kind of said that. It's got -3 attached to it, but what else? What else? Right? Something else is going on here as well. Right? If I look over on this side, there's another value at 4 that seems to hit -1 as well. So this is actually 2. There's 2 values of x that give me this same y value. So one was -3. We saw that right here. But the other one is +4. So we would say, that x could be either of these 2 values. Is this a function? Well, yes, it's a function, right? If we look at vertical lines, no vertical line hits this in more than one spot. So we would say, yes, this is a function. Just because it didn't pass the horizontal line test, it hits a horizontal more than one value for -1 here. A horizontal hits in more than one spot. That's okay. That's okay. We're talking about a vertical line test to indicate a function. One value for every x input gives you a single value of an output. Just because those are repeated values is irrelevant. So yes, this is a function. So now we're supposed to determine some more of these values here. Um, I would say that this y-intercept is a little bit less than whatever that tick mark is, and it looks like the tick marks are in terms of 4s. So that might be, I don't know, a quarter of the way from 4 to 8. So I'm going to say this is approximately 5. Very hard to see on this graph. What about the x-intercepts? Well, where does it hit the x-axis? One right here and one right here. So we'd say the x-intercepts are minus 1, excuse me, and 5. What about the domain? Well, the domain is actually everything. It goes off in this direction, off in this direction. No, this is looks like a cubic polynomial. Polynomials always have outputs sorry, for every input. So just either from the trend of this graph or from knowing that this is most likely a cubic curve, right? We're going to say that the domain is all of the real numbers. And look at the range, right? The range too. Well, all of these low guys hit all of these very low values, and then up to some value here, and then goes back down again, my y values, and then up again, and now it increases without bound, just keeps on going up. So actually, and this is true of all odd polynomials, the range, odd degree polynomials, the range is negative infinity to positive infinity as well. What about these expressions? What is minus 3? That's right here. Kind of hard for me to see where that is. I think it's at minus 32. What about minus 1? Oh, well, that we see it's got a y value of 0 because it hits the x-axis. And what about 4? That's right here. I'm having a hard time with that one. It looks like it's something between these two values, so I'm going to guess that this is minus 25. Again, very hard to see on this graph. I don't much care for that. It's a little bit too hard to make out what the values are along the y-axis to really get good answers for these questions that they're asking. Okay, so here we have a company that has a fixed cost, $45,000 per month, and $70 to produce each stroller that they make. Stroller company. The total cost for the company is the sum of these two. Okay, so let's come up with an equation for that, right? We've got $45,000 plus a variable cost of 70, where the number of strollers that I produce, which they have given as X, I'm going to multiply it by 70 because for every one stroller, I need $70. So these are our total cost functions. What happens when we plug in 100? Well, when I plug in 100 times 70, that's going to be 7,000 plus 45,000 is 52,000. When I plug in 50, right, we're going to have, I'll write this over here. This is 45,000 plus 70 times 50. 7 times 5 is 35. So this is 3,500. And we add that to 45,000 to get 48,500. Thus, it costs, 52K and 48.5. Wait a minute. Hang on a second. I think I put way too many zeros here. This is not 485,000. My God. Costs 10 times as much to produce half as many strollers. No. This is 48,500. All right, so here we have kind of a curious relation. What are the values of x that are getting used? Well, there's nothing over here, right? Nothing happens, and there's nothing over here. Nothing happens over there. The only values that are getting used are between this value of x at -1 all the way up to 3, and we're not even using 3. So your domain in this case is only -1 up to 3, and then it stops. And it stops before 3, use the parentheses. What about my range? Well, my range seems to go as low as 5, but it does, or -5, but it doesn't include it, right? This is an open circle here. So it doesn't include that -5, but it includes all the numbers bigger than that, all the way up to the highest y value attained, which is here at 4. And I'll just say, every time you have one of these humps like this, it really is going to hit the 4 that it looks like it hits. So that's going to be what? From -5 up to 4 inclusively. What is the x-intercept? The x-intercept is where it hits the x-axis at 2. What is the y-intercept? The y-intercept is where it hits the y-axis at 4. Ah, cool. So now we're going to talk about increasing and decreasing a little bit. So increasing means that as you go to the right, the function goes up. If you go to the right and you are going down, the function is decreasing. So let's see if we can figure out where these things are doing what. And I will shade the x-axis red if it's decreasing. And I am going to shade the axis green if it is increasing. So as I go along from the left side here, right, as far as I can see, and I go to the right, I'm traveling up to stay on the curve. And that's true all the way until -7, where it stops. It is neither increasing nor decreasing. At that point, it is turning. And it turns down and starts to go down as we go to the right. So it's negative on this component, all the way up to -5, at which point it is neither. And then again, it seems to pick up and go positive. It is increasing now, going up as we go to the right, and that appears to continue. Now, if it goes off the edge of the map, you just continue as if it just continued its pattern. So what is the interval on which it is increasing? Well, it appears to go from all the way as far left as we can go, up to 7, -7. And it seems like it does that from -5 up to positive infinity. On the other hand, where is it decreasing? Well, just in this middle gap here, just between these two values, is it decreasing. So we would say it's from -7 up to -5, and non-inclusive on either one. We don't include the endpoints because it's neither increasing nor decreasing at these things. Where is it constant? It's not constant. This function is never constant. If it had a flat line component somewhere, that would be where it was constant. But this one isn't. Relative maxes and mins. So a relative maximum is quite simply where it has a peak, a local peak. It's increasing and then it's decreasing. This is a maximum. On the other hand, a minimum can be found in the opposite situation, where is it decreasing and then goes increasing, right? Goes from decreasing to increasing, then it's a minimum. So they want the x values for the relative maximum here. That's -7. And what is that maximum? That's the next question. Well, that's 5. What about the x value of the relative minima? That seems to be happening at -5. And what is the value of that minima? That is to say, what value attained that? Well, that appears to be at +4. Here we have a new example. Where is this thing increasing? Well, it appears to be increasing from this entire left side of the graph. As you go to the right, it travels up, all the way up to 2. And then what about decreasing? Well, it doesn't appear to be decreasing anywhere. And finally, what about constant behavior? Well, it's constant. It's the constant value minus 3 all along this positive region here. So I would say from, minus 2. From minus 2 up to infinity, it is constant. It gives you a single value. It doesn't go up or down. It's just minus 3. So here we have a situation where we're going to be talking about sort of the symmetry of functions. And symmetry is sort of divided into these two big categories for now, right? We want to talk about what we call even functions, where notice that if I have a positive or negative value for x, the same value is selected for y. And geometrically, what that will relate to is having mirror symmetry across the y-axis. Same y values on either side, then we get the same shape on either side of this mirror. On the other hand, this one is rotational symmetry. If I take this and rotate it by 180 degrees, what I will wind up with is the same graph, right? If we take this top lobe here and we sort of swing it down 180 degrees around the origin, right, rotating around this center point, we get the same graph now down on the negative side. And what that 180 degree rotation corresponds to is having the x value change the sign from 8 to its negative when it changes. So we have a function definition for each one of these. It is even if f of x, f of negative x is equal to f of x. It doesn't change. On the other hand, it is odd if f of negative x pulls out a negative sign and gives you negative the value when x is positive. So this one's a little peculiar. If I wanted to look at the y value in terms of x, I would first have to take the x and subtract 1 from it, and then I'd have to get rid of the square, which would be plus and minus the square root of this number. So this is not a function, right? Because when I write it as f of x, I get 2 values. And if I were to take a look at this, what would it look like? Well, it would look like the square root function, but right shifted. And it would look like positive and negative that. And notice that doesn't have 180 degree symmetry. It has symmetry with respect to the x-axis, yes, but that doesn't make it an even function, right? In fact, it's not a function at all. There's no symmetry about the y-axis or the origin. So we wouldn't classify it as even or odd, and we wouldn't classify it even as a function because it fails the vertical line test. What about my x squared plus 1? Well, this definitely is a function, right? And if I graph it, it's pretty easy to see that I just have a parabola that's been upshifted. Notice that if I say f of x is equal to x squared plus 1, and then I say, well, what is f of negative x? Well, that's negative x squared plus 1, but negative x squared is the same as x squared. And so this is just the original function again. Hence, this thing is definitely even. Lastly, right, what happens if I plug in negative x into this one? Well, if I plug in negative x, right, first of all, this is a circle with radius 3. And so, no, it's not a function. Fails the vertical line test, right? If you went to go try to write this as a function of y, right, this is plus minus the square root of 9 minus x squared. And so that's no good. That doesn't give us a function of uh, x. And also notice what happens if I plug in negative x. I get reflective symmetry. This is both even and odd. It has reflective symmetry, right? So it's even. And because I also get the negative value when I plug this in, right, we also wind up with odd symmetry. If you plug in negative x, you get two values. You get the y value of reflective symmetry, but you also get its negative, which is 180 degree symmetry. So yes, it's in fact 180 degree. It's a circle. It's perfectly symmetrical. So we wind up with something like we wind up with even and odd symmetry in this case, even though it does not qualify as a function. We still have this highly symmetrical object. So let's talk a little bit about piecewise functions, and I think that's where I will repair for the day, and I will not go into the transformations of functions until we get on to the next class. But I think we can talk about these piecewise functions now and wrap it up. Let's say that I have a something that looks like this. This is called a piecewise function, and it gives you two different sets of rules. Notice it says if I have x less than 2, and then also if I have x greater than or equal to 2. So basically, you do this when this is true. So we could think about the domain as being cut into two pieces. The thing that I do when x is less than 2, so where's 2? Right here, right? And then let's graph this thing, x squared minus 3. Right, I'll actually kind of skip a little bit. This is going to be something more easily seen in the transformation of functions section, but this is going to look like x squared flipped upside down and then subtracting 3 from each one of those values. So here is my negative parabola all the way up to 2. I have something that looks like this. You could also imagine plugging things in. Plug in 0, you get minus 3. Plug in 1, square it, and then subtract it, you get minus 4, and then minus 7, and so on. What about for the values greater? That was this part. What about for values larger? So for values larger, it says we do 7 minus 3x. Well, where would that be at 2? That would be plugging in a 2 here. 7 minus 3 times 2. That's minus 1. So that's way up at here. Minus 1. And I want to do something. So this is less than or equal to. So I'm going to shade this one in. This other one I should leave open because it is not really attaining this value, right? It's only when it's less than 2, not at 2. So we could leave that open. And then this has a slope of minus 3. So we can go to our next point on this second half of the graph by going over 1 and down 3, over 1 and down 3, over 1 and down 3. Right? So these points are on our graph. So on. And let's make this a little thicker so that we can actually see these bad boys. Went a little too far there. Let's try that again. So something like that. So when we think about these piecewise functions, right, we're going to think about functions who have certain rules on certain intervals. Here, for the values less than 2, strictly less than 2, I'm going to do one thing. And then for values strictly greater than 2, or greater than or equal to, I should say, we're going to do something else, right? And then we put those two graphs together. What is the domain of this function? Well, actually, every single x value is covered, right? We know what to do for all the values, including 2, where it splits the rules up. What about the range? Well, the highest value that gets hit is -1, and the lowest values are, well, it just keeps on going down. What is f of 3? Plugging in 3, we would get -4. What about -2? Plugging in -2, we would get 3, 4, and then down to 7, I believe, -7. And then it says find all the values where f is equal to -2. All right, well, -2 is right here. There's nothing on the right-hand side, but over here I have a single x value for which that would be true. So I could go and look at the equation there, right? Y equals, in the green region here where we see an intersection, right? This is 7 minus 3x. And then I'm asking the question, when is that -2? I know to use this one because I can see my only intersection is over here on that green curve. And then rearranging things here, right, I get -9. Did I graph this wrong? Hang on, let's go back. 7 minus 3x. If I plug in 2 here, I have graphed this wrong. Oh, bullocks. I did graph this wrong. What is 7 minus 2 times 3? It's not -1, it's +1. So actually, let's fix this graph real quick and also change the answers that need to be changed. Never be afraid to go back and redo some of your work if you discover a mistake, right? This actually starts up here at +1, and then by the time that I go down to this one, it is at -2 when I'm at 3, and so on and so forth. Now it goes down as follows. This is actually our graph. And so actually our range needs to be corrected. This goes all the way up to +1, yes. And f of 3, right? This is also something that we've goofed on. F of 3, actually, if I plug that in right, I would have 7 minus 3 times 3. And then that's going to be -2. -2. So yes, where is this at -2 when the x value is 3? And that's what we found over here. If I were to push this home, right? This says that when y is -2, our x value is given by this term. Oops. And, finishing that solution, we have x is equal to 3. All right, let's stop for here, and we will continue on with more of these at a later class.